All right, now we are going to continue section 3.1. In the previous video, I showed you what are systems of ODEs, and in one example, we modeled a physical process. We modeled a physical process with two ODEs. Now, in these coming examples, we are going to see why systems of ODEs are useful. Okay. All right. So let me share my screen. Okay, this one. All right. Okay. First of all, okay, as you may remember, if we have a first order differential equation, it is easier to solve, right? But if we have a higher differential equation, it's getting more difficult and difficult to solve. One good news is we can, whenever we have a higher order differential equation, we can represent that differential equation, that higher order differential equation, as first order differential equations, actually a system of first order differential equations. Okay, so if we have third order differential equation, if the order is 3, then we can rewrite this differential equation using 3 different first order differential equations. Okay, so instead of working that third order differential equation itself, we can work on the 3 first order differential equations, and it is easier to solve them. Okay, so in these examples, we are going to talk about that fact. So as I said here in the note, differential equation systems of DEs containing higher order derivatives. Oh, I have to pick the my son is calling me. My sons are actually calling me. Anyway, so we can represent higher order derivatives as first order systems by introducing new unknowns. Okay, so first let's look at this example. We already know this differential equation, right? It's the spring mass equation with no external forces. Now let's try to rewrite this as a system of first order DEs. Okay, first of all, what is the order here? What is the order here? Order is 2, right? So I can rewrite this equation, this second order differential equation, using 2 first order differential equation. Okay, all right. So what are they? First of all, okay, let's say x prime is equal to y. Okay, that's why I can rewrite x double prime as y prime, right? Okay, so what is our first order differential equation? I can plug this here, right? So m y prime plus cy plus kx, I don't do anything for x, is equal to 0. And what is the order of this differential equation? 1, right? Because the highest derivative is 1. And the second first order differential equation is already here, right? So y is equal to x prime. Okay. Now I can use these two first order differential equation to solve that second order differential equation. Okay, same. What we are doing here is actually nothing but we are just introducing new unknowns, introducing new variables, and try to reduce the order of the differential equation. Okay. All right. And in general, if we have an nth order differential equation like this one, this is a general formula, right? We can rewrite this as this way, and this time let me use another. Okay, and there is a abuse of notation here in the previous example, right? X was the dependent variable name and the time was the independent variable. But in this case, the x is the independent variable, and the y and y prime, y double prime, all those y variables are the dependent variables, okay? So, all right, let's say y1 is equal to, y prime is equal to, or maybe I can even, instead of y, I can say, let's say u1 is equal to y, okay? I'm introducing a new, I'm just calling u1 is equal to y. So what is y prime? u1 prime. So let's say u1 prime is equal to u2, as I did in the previous example. It's first, or let's call first derivative is u2. And in similar fashion, u2, don't do that again. u2 prime is equal to u3. And keep going that, okay? And the last thing I can say, u n minus 1 prime is equal to.
So n, and of course un prime, this is y of n, right? So n prime is equal to f of
u n minus 1. It goes like that. I'm just plugging these values here, right? These unknowns here, u2, u1, and x. Okay. Apart from this first guy, right? This is just, I'm just renaming y as u1 to make it all u's. Okay. Look at these differential equations. How many differential equations are there here? 1, 2, 3, all the way through n, right? So there are n differential equations. What are the orders? They're all first orders. And now I have, since this is a differential equation with order n, right? Nth order differential equation. Now I have n first order differential equation. So I'm representing this differential equation here in the example as n different first order differential equation. In other words, I'm representing this nth order differential equation as a systems of a first order differential equation. Okay, makes sense? So instead of solving this guy, you can solve this one, and whichever easier is actually, you can use whatever you want, whichever you want, okay? So now I could represent all these guys with n. Okay, let's look at this next and last example in this section. So let's solve the system of equations with below with initial conditions x of 0 is equal to 1 and y of 0 is equal to 0. And I can reverse the process, okay? In this case, I have two first order differential equation, and I can rewrite these two equations, these ODEs, two ODEs, as a one differential equation with second order, okay? First of all, what we have here is y prime is equal to x, right? And y double prime will be equal to x prime, right? So I can take, I'm using the second given equation, and I am finding x prime. Now I'm going to plug this one in the first equation, okay? So what we will have here is y double prime is equal to 2y minus x, and x is y prime, right? X is y prime. So I can rewrite this y double prime plus y prime minus 2y is equal to 0. Now we get second order homogeneous differential equation, right? And we know how to solve. these equations very well using the characteristic equation. So what is the corresponding characteristic equation here? R squared plus R minus 2 is equal to 0. And if I factor out R and minus 2, I can factor out as plus 2 minus 1, right? It's equal to 0. That's why R is equal to minus 2 plus 1. So what are the solutions then? Y is equal to C1 e to the minus 2t plus C2, these are constants as you know, e to the t. Okay, is this the answer? No, right? I want to solve x. Okay, so, but I know that x is equal to y prime, right? So x is equal to y prime. That's why just take the derivative of it, right? So if I take the derivative here, I have to use the chain rule, right? So derivative of negative 2 is negative 2. So it will be negative 2 c1 e to the negative 2t plus, and derivative of this part will be itself c2 e to the t, right? And this is an initial value problem. We have the initial values, right? So we can use those initial values. X of 0 is 1. Okay, so if I plug it in 0 here, for each t, it will be equal to 1, right? Negative 2. And if I plug it in 0 here, right, it will be just e to the 0, which is 1. It is negative 2c1 plus c2 is equal to 1. And the second initial condition y of 0 is equal to 0, right? So I'm gonna use the previous equation, right? Just plug it in 0 here. It will be c1 plus c2 is equal to 0. Okay. All right, let's solve it. Let's multiply everything with negative 1 here. Negative. Why does it write? Negative. This will be also negative, right? Negative 0. I can maybe move it a little bit higher. So if I sum them up, negative 3c1. Come on. Negative 3c1 is equal to 1. C1 is equal to negative 1/3. And if you look at the second equation, C2 is just negative C1. So C2 is equal to 1/3. So the solution is then x is equal to, just plug it in these guys here, right? 2/3 e to the negative 2t. And C2 is 1/3, so plus 1/3. Let me make it a better 3. E to the t. All right, this is the solution. All right, this is the end of this example and end of in this section. The end of this section. We are gonna start 3.2 in the next section, next video. All right, take care, guys.